In this lecture, we are going to deal with the second part of data transfer instructions present in ARM. Till now, we are seeing the pre-indexing where the address was incremented by an offset value. Now, we are going to see an instruction where the address location will be decremented by an offset. So, again, we will see the example. This example we have seen before. So, now you can see that I am writing an instruction LDR R0, 40004. What does it mean? This constant address you are moving to R0. So inside R0 you are having an address 4004. Previously it was 4000. But now for time being I am moving an address location 4004 into R0. That means R0 is pointing to 4004. The next instruction I am moving the content of the pointer R0, that is the content of address location pointed by R0. I am moving to R1. That means this data I am moving to R1. So R1 will be having what data? This data, right? So R1 will be having this data. Then in the next instruction I am writing LDR R2, bracket R0, hash -4. So only difference is there. Instead of 4, I am writing -4. So since I am writing hash -4, what does it happen? Whatever address is stored in R0, that will be decremented by this offset value. Till now we are seeing only the incrementing operation on the offset value and the base address. But now this base address stored in R0, that is 4004, will be decremented by 4 since minus is there. So now what will happen? This pointer will be decremented by 4. So it will go back to 4000. Right? So now my R0 is pointing to 4000. Why? The previous pointer was here. I have decremented the base address by 4 unit. So when you are subtracting 4004 minus 4, you will be getting 400. That means now my R0 is pointing to this address. And the similar operation will be done. Content of R0 will be moved on to. So now you can see that the address was decremented to 4004. Previously it was 4004. Now the address was decremented to 400, right? And whatever content is present in this address will be loaded to R2, right? So address will be decremented by 4. So previously the address was 4004. After decrement operation, the address will be 4000, and since write back is there, the decremented address will be updated in R0. Previously R0 was 4004. Since write back is there, it was decremented by 4, and decremented address it is written back to R0, and the content of that address will be moved on to R2. So what will be content of R2? 101010. So what is the difference here? Instead of incrementing the base address by 4, since it is a -4, you are decrementing the base address by 4. Initially the base address was 4004. After executing this, what will happen? 4004 will be decremented by 4 and the address will be updated. So instead of 4004, it will be storing 4000 in R0, and the content of that updated address, that is this data, will be moved on to R2. So this is how you are performing decrementing operation on the by using the offset value, right? So how will you do that? Minus sign should be added to the offset. So what is it known as? Pre-indexed addressing mode with write back. What type of indexing you have done? Decrementing operation you have performed. The addressing mode remains the same, but the operation you have done was, the indexing you have done was decrement operation. In the next example, we are going to see how will you give the offset value in a register. Till now we are using immediate offset. The offset was directly given in the instruction itself. But here in this instruction, let us take this example, LDR R3 comma bracket R0 comma R2. Previously what I have done, I have written R0 comma hash 4 or hash minus 4. That means the offset value was directly present in the instruction itself. That is why it is known as immediate offset. But here you can see that the offset value will be present inside another register known as R2. That is why it is known as with register offset. Whatever offset I need, that was stored in another register known as R2. So now in R2 what I am having? 0004. So this is my offset. So here what will happen? Base address is stored in R0. What is the base address? 4000. To that base address, you will add the offset present in R2. What is the offset? 4. So, you will be adding 4000 plus 4. So, what will happen? Your R0 will be pointing to 4004, right? And R0 will be updated with the new address. Why? Because write back is there. So, now you have added the base address present in R0, that is 4000, with the offset present in R2, that is 4000 plus 4, you will be getting 4004. That means R0 is pointing to 4004, and since exclamation was there, the new address was updated in R0. Content of the memory address pointed by R0. What is that? 202020. That will be moved on to R3. Right? So operation is same, but only difference is that the immediate, instead of immediate offset value, you are having the offset value in another register known as R2, right? And the content of the address location pointed by R0, that is this content, will be moved on to R3. So R3 will be having this data. Only difference is that the offset value was stored in another register known as R2. That is why it is known as, and the address will be updated. So it is known as pre-indexed addressing mode with register offset along with the write back. Right, only difference is in the register offset. In the next example, we are going to see another addressing mode known as scaled register offset. In the previous example, we have seen that the whatever offset value you want to store, that was stored in a register. And here in this example, what is the example? LDR R3 comma R0 comma R2 comma LSL hash 2. This scaling factor also I have added here. What is LSL? Logic shift left hash 2. 2 times you need to perform logic shift. So why it is known as scaled register offset? In our case, my offset value is present in R2. That offset value present in R2 will be left shifted by 2 units. That is why it is known as scaled offset. Right? Whenever you are left shifting a value, you are actually scaling it or actually multiplying it by 2. Right? So in my case, what is the content of R2? 0001. My offset value is 0001. When I am left shifting this 1 by 2 unit, what you will get? 1 by 1 unit you will get 2. 1 by 1 more unit you will get 4. Right? So 1 you are left shifting by 2, so you will get 4. So my offset value is 4. That offset value I will be adding with the base address, that is 4000. So when I am adding 4 with 4000, what I will get? 4004. Same address what you have seen before. So now my R0 is pointing to 4004 and the base address present in R0 was updated with the 4004 since write back is there, right? So only difference between this instruction and previous instruction was you have added a scaling factor here. So R2 was holding the offset value, that is 001. That data you are left shifting by 2. So 1, when you are left shifting by 2, you will get 4. This 4 you are adding with the base address. So 4000 plus 4 will be getting 4004. Right? Then since this bracket is there, what will happen? The data pointed by R0. What is the data? 2020. That data will be moved on to R2. Right? So this 202020 that will be moved on to R3. Right? So whatever data you have which is present in 4004, that will be moved on to R3. So only difference is here, it is a using scaled register offset. Your offset was there in R2, that offset was scaled by using this part, and by using the scaled offset you are updating the base address to 4004, and whatever data is present in that updated address value, that data will be moved on to R3. It is known as pre-indexed scaled register offset with write back. The new term is scaled because you are scaling the offset value stored in R2. The next instruction you are, till now you are dealing with the single register load operation. So single register load means you are loading a word of data. But in this case you are going to see how to load half word data. Half word means 16-bit data. How will you store or load 16-bit of data? Now we are going to see how to load half word. Right? So same instruction we will see LDR R0, 4004, but the next instruction is LDRH. LDRH stands for you are going to load half word. Right? If you are writing LDR R1, bracket R0, you will be loading one word of data. But here since H is there, you are going to store only half word of data pointed by R0. What is the data pointed by R0 now? 10101010. Right. So since LDRH is there, you will be loading only half word of data. What is a half word? 16 bits. So only the LSB 16 bits will be loaded onto R1. Right. Only LSB 16 bits, that is a half word, will be loaded onto R1. What will be the remaining bits? It will be zeros. It will be zeros. Only 16 bits will be loaded from this address. Remaining bits will be zeros. Then in the next address you are incrementing this R0 by 4 by an offset 4, and again you can see that it is LDRH. So what will happen? R0 will be incremented by 4. So 4000 will be incremented by 4, that is 4004, and the data present in this updated address will be loaded to R2. But again, since it is LDRH, only 16 bit will be loaded. Remaining 16 bits will be zeros. Right? These MSB 16 bits will be zeros. Only LSB 16 bits will be loaded. Why? Because you are using LDR half word, load half word instructions. Next one is, so here again you can see that write back is not there. So R0 will be 400 itself since write back is not there. So it is known as base plus offset with the pre-indexed addressing mode. The addressing mode remains the same. Only thing is that instead of loading a word, you are loading half word. In the next instruction, you are going to load a byte of data. Previously, you have loaded half word. Now, we are going to load a byte of data. So, I am writing LDRB R0, bracket R0. So, my change is here I am writing LDRB. B stands for byte. So, what will happen? Your address location pointed by R0 is 400. Whatever data is present in that will be moved on to R1. The operation is same as LDR, but since B is there, what will happen? Only the LSB byte, only 1 byte or 8 bits will be loaded onto R0, R1, right? Only 1 byte of data, LSB byte, that is 8 bit, LSB 8 bits only will be loaded. Remaining all the other bits, that is remaining 3 bytes, that is 24 bits, will be zeros, right? Any doubt? So since you are using LDRB, only the 8 bits, LSB 8 bits will be loaded onto R1, remaining 24 bits will be zeros, right? Similarly, I am writing LDRB R2, R0, hash 4. That means my address will be incremented by 4 and whatever content is present in this address will be moved on to R2. But again, since it is B, only the LSB byte will be moved. All the other 24 bits will be zeros. And since you are not using any write back, R0 will be containing the base address itself, because write back is not there. So R0 will be containing this address itself. So this is how LDRB operation is done. So, and it is coming under the same addressing mode. Only thing is that instead of moving word, you are moving byte, right? Then in the next example, we are going to load signed half-word. Previously we have done what? Simple half-word means it is unsigned. But here you are going to move signed half-word. So how will you refer to a sign of a number? The MSB most bit will be representing the sign. If the MSB most bit is 0, that means it is a positive number. If the MSB most bit is 1, that means it is a negative number. So here you are going to perform signed half-word operation. So how will you refer to that? LDR SH. SH stands for signed half-word. SH stands for signed half-word. So you are going to move signed half-word, right? So again you are going to move the content of address location pointed by R0. So what is the content of address location pointed by R0? In this case 1010 FF10. You are going to move this data to R1. But since you are using half-word, only how many bits? 16 bits will be moved, or half-word will be moved. And here again, since if you are moving half-word, the 16 bits will be moved, remaining bits will be zeros. But here you should keep in mind you are using LDR SH. That means sign bit will be preserved, right? So you are performing sign bit extended version of half-word will be moved. So you can see that your half-word will be as it is FF10, but the remaining 8 bits, remaining 16 bits will be 1111. FF stands for 1111. Remaining 16 bits will be 1111. That means you have performed sign extension on the sign bit. Why? Because in this case, if you are taking this half-word alone, what is the MSB bit? If you are taking this half-word alone, MSB bit will be 1. So if you are moving this half-word alone, MSB bit will be 1. So that sign bit will be put for all the other 16 bits. That is known as sign extension. In my case, my sign bit was 1. That shows that my half-word is a negative number. So that sign bit will be copied onto all the other remaining bits. That is known as sign extension. That is how you are getting FFFF, then your half-word. Similarly, in the next instruction, what I have written, LDRSH R2, R0, hash 4. What does it mean? R0 address will be incremented by 4, right? And whatever data is present in that incremental address will be moved on to R2. Since it is half-word, 16 bits only will be moved. But here what you will be getting? You will be getting 2020, that is half-word, and remaining bits will be zeros. Why the remaining bit is 0? Here also you have performed sign extension. But why it is 0? because if you are taking this half word 2020, what is the MSB bit? 0, because 2 means it is 0010. 2 means it is 0010. So what is the MSB most bit? 0. So if you are taking this half word, MSB bit is 0. That shows that this half word is a positive number. So since you are performing sign extension, since you are using LDRSH, that sign bit, that is in our case sign bit was 0, that sign bit will be extended for all the other bits, right? That means all the other 16 bits will be copied with the sign bit of this number. What is the sign bit of this number? 0. So all the other 16 bits will be written with zeros, right? So if you are using LDRSH, what does it mean? Half word will be loaded and the remaining 16 bits will be copied with the corresponding sign bit. In the first case, the sign bit was 1. F means 1111. That means the MSB bit will be 1. That sign bit will be copied on to all the other bits. That is why it is known as sign extension was performed on this half word. Similarly, for the second number, the MSB nibble is 2. 2 means 0010. So the MSB most bit is 0, that is sign bit is 0. That 0 bit will be copied on to all the other bits, right? So whenever you are using signed half word load store, what will happen? The half word will be loaded and the remaining bits will be sign extended value of that half word. You should keep in mind, if it is a negative number, that 1 will be copied on to all other bits. If it is a positive number, 0 will be copied on to all the other bits. But if you are using LDRH alone without S, what will happen? The remaining 16 bits will be always zeros. If you are using LDRH, then the remaining bits will be always 0. Sign extension will not take place. All the remaining bits will be zeros itself. The next, so here again, since write back is not there, R0 will not be updated, right? And the offset, the addressing mode is same as this itself. Only thing is that you are using signed half-word. In the next operation, you are using signed byte load. Previously you have seen unsigned byte. Now we are going to see signed byte. So LDRSB. So again, whatever data was present in 400, that will be moved on to R1, but only one byte will be moved. Here what is a byte? FF. FF will be moved and the remaining all bits will be, what is the MSB bit of this FF? In my case it is a byte of data. What is my MSB bit? In this case 1. Right? That means my sign bit is 1 and all the other 24 bits will be sign extended. 1 will be copied onto all the other bits. Why? Because you are performing signed byte operation. In the next example, you are incrementing R0 by 4, right? So resultant address will be 4004. Whatever data is present in this will be moved on to R2. Since it is byte, the last byte, that is 20, will be moved on to R2 and remaining bits will be zeros. Why it is 0? Because in my byte of data, the last bit is 0 because 2 is represented by 0010. So if my data is 20, my MSB bit is 0 and that MSB bit is known as a sign bit. That sign bit will be copied on to all other bits, all other 24 bits. So since you are using signed byte operation, the sign bit will be extended or sign bit will be copied on to all other bits, right? So it is same as signed half word, but only difference is that you are moving byte of data. And again here you can see that the write back is not there, so the address will be 400 itself, right? And the addressing mode is same as before, only difference is that you are performing signed byte operation, right? So these are the different types of load and store operation you can perform using data transfer instructions. Next we will see an example. Let us take R0 is having this address 000, R1 is having this address 9000. So memory 32 of 900, what does it mean? This address is containing a data 010101. Similarly, this memory location, that is 9004 memory address, is containing this data. So 900 address is having this data, 9004 address is having this data, right? Then I am writing an instruction LDR R0, R1, #4 exclamation. What does it mean? R1 will be incremented by 4. Content of that address will be moved on to R0. This is known as pre-indexed addressing mode with the write back. So what will be the content of R0? What will be the content of R0? R1 will be incremented by 4. So what was R1? 9000. Content of R1 was 9000. This will be incremented by 4. So you will be getting 9004. So your resultant address is 9004. Content of this address will be loaded onto R0. So what is the content of this address? That is written here. Memory 32 of this address equal to this data. Right? So this data, that is 0202, this data will be moved on to R0. So what is the content of R0? 020202. Then what will be R1? What will be R1? Whether R1 will be updated or not. Initially R1 was 900. Now you are incrementing R1 by 4. And since exclamation was there, write back is there, R1 will be updated by 4. So previously R1 was 9000. Now R1 will be 9004. Next let us see next example. Writing LDR R0, R1, #4. Exclamation is not there. It is known as pre-indexed addressing mode. Write back is not there. So what will be the content of R0? R1 is having this address 9000, right? R1 is having this address. Now I am not considering the first instruction, I am considering only this instruction. So when I am considering this, what is the content of R1? 9000 itself. To that 9000 I am adding 4. Now the address location is 9004. Content of that address location I am moving to R0. So what will be R0? Content of this address location. What is that? 020202. So content of R0 will be this data itself. Right? So in both the instruction you are getting the content of R0 as same. But what will be the content of R1? Since exclamation was not there, the content of R1 remains the same as initial address itself. Initial address was 9000 itself. So the address of the content of R1 will not update or will not change. Since write back was not there, the address present in R1 will be 9000 itself. Now we will see the next example. This is known as post-index addressing mode. So why it is known as post-index? Operation will be done first. What is the operation? Loading will be done, then only the indexing will be done. Loading will be done, then only indexing will be done. That is known as post-indexing. Right. So here what is the operation? Content of address pointed by R1. What is the address present in R1? Initial address 900 itself. Content of this address location, what is that address location? Content 100010101001. That data will be moved on to R0. So content of address location pointed by R1. What is the address location pointed by R1? 900. What is the content of that address location? 010101. This data will be moved on to R0. So what will be R0? 010101. You can see here. Right? Previously the R0 was the content of updated address. That means indexing was done initially. But here loading will be done with the base address itself. Right? So the content of R0 will be 010101. And after performing the load, address will be incremented. So now what will be the content of R1? Address will be incremented from 9000 plus 4. So R1 will be 90004. Right? So in the case of post-indexed addressing mode, even though you are not specifying the exclamation, address will be updated. Base address will be updated. You should keep it in mind. In the case of post-index addressing mode, even though exclamation is not there, base address will be updated. So now R1 will be having 9004. This is a small example showing the operation of LDR. Then we will see the summary of all the LDR instruction what you have seen till now. Or these are the different addressing modes used in load and store. First one is LDR R0, equal to 0x400. This is known as immediate addressing mode. Why it is known as immediate addressing mode? Data is present inside the instruction itself. So this data will be moved on to R0. Second one, you are writing LDR R1, bracket R0. What does it mean? It is coming under addressing mode known as base plus offset addressing mode. What is the base address? It is stored in R0. What is offset here? In this case, offset is 0. Right? So LDR R1, bracket R0, what does it mean? Content of 4000, right? Content of the memory location pointed by R0 will be moved on to R1. Right? And one word of data will be moved. Why? Because it is LDR. That is why it is written memory 32. One word will be moved from this address location to R1. In this case, what will happen? The base address will be incremented by an offset known as 4. So the base address will be added with the offset to 4, and one word present in that updated address will be moved on to R1. The next one, instead of writing hash 4, I am writing hash minus 4. So what is the difference between this and this? Instead of adding the offset, in this case offset will be subtracted from the base address. So base address minus offset, that is minus 4, and content of that resultant address will be moved on to R1. Here, instead of writing immediate offset, you are storing the offset in another register known as R2. So how the address updation will be done? Base address plus the content of R2. Content of R2 is nothing but offset. Whatever content is there in R2, that will be added with offset, and with that, from the updated address location, the content will be, or the data, or one word of data will be moved on to R1. In this example, instead of writing R2, I am writing minus R2. So what will happen? The base address will be subtracted by R2. So 4000 minus R2 will be the updated address. From that updated address, data will be loaded onto R1. Here, what is having? I am using something known as scaled offset addressing. This offset address I am scaling by 2. That means the base address will be added with the offset scaled by 2. Where is the offset present? Offset is present in the register. That present offset present in register will be left shifted by 2. That is scaled value of offset will be created here. That scaled value of offset will be added with the base address, and that will be the updated base address or updated address. From that updated address, data will be moved on to R1. Then here, instead of plus R2, I am writing minus R2. So only difference is that the scaled address will be subtracted from base address. Base address minus R2 left shifted by 2. Here it was base address plus R2 left shifted by 2. And from that address, data will be loaded onto R1. Here I am writing LDRH. So what does it mean? Only half word of data present in this address, 16 bit of data present in this address will be moved on to R1. Next one is LDRB. So only 1 byte of data present in this address will be moved on to R1. That is memory 8. 1 byte only will be moved on to R1. Only 8 bits. In the previous case, Halfword 16 bits will be moved on to R1. Next one is LDRSH. That means sign extended Halfword will be moved on to R1. Whatever data is present in this, right? Whatever data it may be, you will be moving only sign extended Halfword. You will be, even though you are having 32 bit of data in this address, you will be moving only 16 bit of data since it is LDRH, and since it is S is there, sign extension will be performed. So signed Halfword will be moved on to sign extended Halfword will be moved on to R1. Here you are performing sign extended byte will be moved on to R1. Sign extended 8 bits, that is sign extended byte present in this address location will be moved on to R1. Last one is store operation. Right? Store operation, what does it do? Whatever data is present in R1 will be moved on to address pointed by R0. Now my address pointed by R0 is this. So content of R1 will be moved on to the address pointed by R0. What is address pointed by R0? This one. So R1 will be stored onto this memory address. So after executing this memory address will be having the data present in R1. R1 will be moved on to this address, right? And how much data will be moving? 1 word. Why? Because it is LDR. If you are writing strh, what will happen? Halfword only will be moved. If you are writing strb, byte only will be stored, right? So for all this operation, instead of LDR, you can replace with str, right? So whatever instruction I have written with LDR, all this instruction is applicable for str also. So whenever you are performing str, movement will be from left to right. Content of R1 register will be moved on to a memory address. So these are how the store and load operation is working. Thank you.